Welcome to, and I'll give you a moment to shed a tear, the final section of the course. This week is only 5.3. Next week is only your final exam. Okay. So you should have plenty of time to study ahead of time for your final exam. All right. So we're going to start by talking about relative rate of change. We got this little definition right here. The relative rate of change. And I really hope you like looking at this because you're never going to see it again. The relative rate of change, which I will often abbreviate as REL ROC. Okay. I love abbreviations. I hate writing really long things like this. The relative rate of change of f of x is f prime of x over f of x. Okay, this is the relative rate of change. It is just how is the function changing? That's the derivative. And then it's relative, like it's normalized. So it's how is this function changing relative to its actual function value at that point. So, something is changing by, $2 every day. If it's the price of a dozen eggs, $2 every day, that's a big relative change. If the price of a Mercedes is increasing by $2 every day, that's not so noticeable. That's why relative rate of change matters and why we normalize it by the value of the actual function in it, like the cost of a dozen eggs today. Okay, so this is a relative rate of change, and the percent rate of change. I had to make sure my percent sign wasn't backwards. Percent rate of change is this times 100%. To go from relative to percent, you just translate to a percent, just like in 5.2, where you made sure to convert your interest rate to a decimal. Percent rate of change, we convert the decimal to a percent. All right. So we're going to start with a nice little example 0, a nice innocent example, nothing going on here. Find the derivative with respect to time of the natural log of f of t. We're going to use the chain rule. Everyone loves the chain rule. People actually hated chapter 4 a lot more than I thought they would, or chapter 3. I thought chapter 3 was going to be popular, but I don't think chapter 3 was very popular at all, but we're going to use the chain rule here. The derivative of the natural log is the reciprocal of the inside, right? The derivative of ln x is 1 over x. So the derivative of natural log of f is going to be 1 over f. But remember, we have to use the chain rule. If the inside is anything other than the single variable, we have to use the chain rule. So we're also going to multiply by the derivative of the inside. Well, what's the derivative of the inside? F prime of t. Well, let's combine this. This is f prime of t over f of t. Oh. Wait a minute. This is the relative rate of change, right? This is the relative rate of change. What a coincidence. Wow, let's get an exclamation point in here. The derivative of the natural log of the function is the relative rate of change. And for this reason, the relative rate of change is often called the logarithmic derivative. We got two words that mean the same thing. Well, a lot of words, two groups of words that mean, two names that mean the same thing. Whew. We're ending on a wacky note. All right. So relative rate of change, logarithmic derivative, they mean the same thing. Okay, so let's use this to solve our actual first example. I sort of tricked you right there. That wasn't really an example. It was just me introducing a definition. I probably fooled you good. Example 1, find the logarithmic derivative. Find the logarithmic derivative. And the percent rate of change at the given t. So part A is going to be our function is equal to t cubed plus 2t squared minus 11, and t is going to be at 1. We specifically care about, okay, how is this function changing when t is 1 relative to its size? So the logarithmic derivative, the relative rate of change, they are interchangeable, is f prime of t over f of t. So we just say, okay, what is f prime? We can take the derivative of this, no problem. Power rule. We are power rule experts. Divided by the original function. Well, the original function, nothing to do here. Let's just write that function again. Right? This denominator is just the original function. Be very careful with your simplifying here. We can only simplify if they have common factors. And honestly, I don't care about simplifying this because we really just want to find what is the rate of change at t. Actually, it does ask you what is the logarithmic derivative. All right, this is the first half of our answer. This is our logarithmic derivative. You could factor it. I'm not going to make you factor it here though. Okay. The percent rate of change at the given t is going to be, okay, what happens when we plug in 1? Right, t is equal to 1 for us right here. So you plug in 1, we're going to get 3 times 1 squared plus 4 times 1, all over 1 plus 2 times 1 minus 11. We simplify that out. It should be 7 over negative 8. And we want to write this as a percent. That's going to be negative 87.5%, I think. And before I box my answer, I'm going to surreptitiously go over to my calculator. Yeah, 87.5%. So at this value of t, this function is decreasing by about 87.5% of the function value. All right? That's how it's changing. Relative and percent rates of change, logarithmic derivatives, all kind of the same thing, is all about just relatively, how is this function changing? Again, if it's a big function, we need a big derivative to be a meaningful change. I don't care if the price of a house is increasing by $2 every day. I do care if my eggs increase by $2 every day. Okay? Need to get those eggs for my cookies and my pancakes and all my other very healthy things. You can also baste eggs, baste egg whites on the crust of homemade pizza. That's very good as well. I need to do that again. I haven't done that for a while. Not relevant to the video. But we'll have more cooking. Maybe we'll have a sequel. The final week, there won't be any math. Maybe we'll have a cooking week. Anyway, let's do part B. Find the logarithmic derivative and the percent rate of change at a specific t value. All right. So, again, there's a couple ways of doing this. There's a really cute way of doing this problem, but I'm not going to be cute today. Let's just do this normally. The logarithmic derivative is f prime of t over f of t. It's the relative rate of change. We need to take the derivative of this exponential function. Chapter 4. Another section that was a little less loved than I expected, but that's okay. It doesn't need your love. The derivative of an exponential function is itself. But don't forget about my buddy, the chain rule. If this exponent is not just a t, we have to multiply by the derivative of the inside. So we're going to multiply by the derivative of the square root of t. And remember, right, t is a square root. Square root has an exponent of 1/2. These are identical. So to take the derivative of this, we use the power rule. All right. So bring down that exponent of 1/2 and subtract 1 from the exponent. Gives us this. Looking a little messy, but don't worry. We're dividing by the original function. We're dividing by the original function, and hey, we got some cancellation. The logarithmic derivative, the relative rate of change, is actually just this guy up here. which can be simplified to 1 over 2 square root of t, using this logic that we used up here. And negative exponent means denominator, or flipped, reciprocal, however precise you want to be. So this is our logarithmic derivative. This is our relative rate of change. So to find the percent rate of change when t is equal to 4, we're going to plug in 4. What is the derivative at 4 divided by the function at 4? What is the slope here? What is the rate of change normalized by the actual size of the function? So that is going to be, we just plug it into our logarithmic derivative, which we just found. 1 over 2 times the square root of 4. That's 1 over 2 times the square root of 4 is definitely 2. Is 1/4, or 25%. 1/4 is 25%. It's 0.25. Turn 0.25 into a percent. Okay? This is the rate of change. So this function, when t is equal to 4, this function is growing by about 1/4 of its size. That's how fast it's growing. 1/4 of its size for every unit of t. All right? 25% increase. And that's the relative rate of change. Go ahead. Enjoy some of these problems. Enjoy one of your last homework assignments. Bye. I never know how to end these, so I'll say bye again.